Hello, I'm Jacob Adams. This is a presentation I gave at the UGIC 2023 conference in Midway, Utah. I recorded the audio of my presentation, but I forgot to start it until about a minute or two into the presentation. So this first little bit is going to be me talking here in the future, and then we'll switch over to the recorded audio. Now, the recorded audio isn't all that great because I was just recording it with my phone, so bear with me. I've tried to highlight some of the key bits of code and everything here in the video so that you can understand exactly what's going on. So, without further ado, let's dive into Preaching Pandas Power for Python Programming Progress. This is an introduction to using pandas in spatial GIS format. Now, I'm going to be throwing a lot of code at you. There are going to be a lot of examples, and it can come pretty fast, especially towards the end. So don't worry, you can download the Jupyter notebook that this presentation was built on and get direct access to the code cells, play around with it, change some things, try things out, and really learn that way. Because really the best way to learn is not by listening, but by doing. So you can get this Jupyter notebook at gis.utah.gov/presentations, which, let's be honest, is probably where you found this video. So why should we use pandas? What's so great about pandas? I've come up with a couple different reasons that really drive why I have pretty much switched over almost exclusively to using pandas in my own programming. The first is that pandas makes it really easy to reference data. In a traditional Python nested list, you've got list within a list, a 2D array. You have to iterate through and say, for the ith row or for the ith element of the jth row, and gets really complicated to remember which one you're actually operating on. And heaven help you if you're using a nested cursor and you have to remember what element, what row. It just gets really nasty. Pandas makes this easy by assigning every row and every column a label, a human or machine readable value that you can use to reference the individual data. This makes it really easy to get at individual rows, individual columns, or even individual elements of your data.
Second is there's a lot less overhead for data management than ArcPy. If you've ever used ArcPy, you have to go in, you have to create a feature layer, maybe you're storing it to scratch or in memory. You have to keep setting that up, breaking it down. There's a lot of processing time involved with setting those up and breaking them down. Pandas is all in memory. You load your data frame, it sits there in memory, you can operate on it, and you never have to write anything to scratch or to disk or anything like that. So it's much faster. There's a lot less boilerplate code that you have to write. As a follow-on to that, it also gives you more readable code because code is read far more than it is written. So if you can make your code easier to decipher 6 months later when you've completely forgotten everything you were doing, that will save you so much time and aggravation. And because there's a lot less boilerplate, once you start to understand the pandas syntax, because there is a bit of a learning curve there, but once you understand it, it becomes much more readable and it's much more concise and dense might be the right word, but you can do a lot in just a few lines of code. Finally, there's a lot of easier interoperability with other libraries. The pandas data ecosystem is very, very robust. There's a lot of stuff going on there. And so you can load data and call other libraries. There's some spatial extensions that we'll talk about so that you can do a lot with pandas.
Just to clarify, I can use anything I can do with ArcPy, I can do with pandas?
Not quite, but almost. Pandas with the spatial extension that either GeoPandas or Esri, you've got full access to most common geospatial operations, joins, buffers. We'll show a spatial join example. So you may have to string together a couple of operations to make it work, but there's a lot of power there. I rarely go back to ArcPy now because I've got this. So we're going to lay our foundation because, like I said, you can read the code all day long, but if you build a house and you don't prep the foundation, the first little bit of rain, the first shift, it's just going to come tumbling down. And that's what I've faced the last couple of years was my foundation was very weak, and so I thought I had it figured out, and then everything crumbles. So we're going to go dive into this. But before we do, just by a show of hands, who considers themselves well-versed in pandas already? Is there anybody who's like really diving into this and comfortable with it? Great. I can tell all sorts of lies and you'll never catch me. Who's played with pandas a little bit? Who's kind of poked around with it? Okay, fair amount. And who's never touched pandas before? Who's new to this? Okay, fantastic. So hopefully this will be a fire hose, but I hope that we really cover the foundation so that you can take this and build on it and learn more. And we'll have a bunch of resources, excuse me, bunch of resources at the end where you can go in and learn more. So first, going to kind of get some of our imports out of the way. That is fuzzy, I apologize. Basic, we import NumPy, we import pandas. We pull in the ArcGIS library, and I'll show that a little bit later why we're doing that. And then we're also going to use path. So we're just getting that out of the way for our examples to work. So first I want to talk about scalars and vectors. Does anybody know the difference between a scalar and a vector and want to explain that to people? Yeah, go ahead.
A scalar is just like a line, but a vector has a point, origin, and direction.
Okay.
Usually.
Yeah, that is a very mathematical definition, right? Or like physics, like a vector is a magnitude and a direction, right? So when we're talking about data, a scalar is just a single value. You could say something like foo. That's a scalar. It just has a single value. Most variables in Python are scalars. Most single variables. So what's a vector? A vector is just a collection of scalars. And when in GIS we think vector like vector line work or vector versus raster. And it's not necessarily that. We're not talking that. We're also not talking, despicable me villains, not victims. It's not vector. We're talking lists. We're talking tuples. We're talking any sort of collection of data. That is a vector. So a scalar is a single point of data. A vector is a collection. So in pandas, sorry, it's fuzzy. Let me see if I can. Yeah. So, sorry, that's the best as I can do. So in pandas, we have two basic data structures we're working with. The first is a series, and the second is a data frame. So a series is just a collection of scalars. And these should all have the same data type, but that doesn't have to be. So we can have a series that we build from a list. This is a series of strings. We can build a series of integers, and we can give it this index, foo, bar, and baz, so that we can reference 1, 2, and 3 by the name foo, bar, or baz when we look at it. And that was that referencing I mentioned earlier. So a data frame is basically a two-dimensional collection of vectors with labels for both their rows and their columns. So it's basically a collection of series for every column. So we're going to build a data frame out of this dictionary where our keys are the column labels and the values are the contents of every column. So we've got the foo column is 1, 2, 3, bar is ABC, and baz is the Boolean true, the float value 1.7, and the string z. So you can see we can have both unified data types, or we can have a whole mixture of data types within a column. And under the hood, again, it's stored as a collection of vectors, of NumPy arrays. And this is one per column. So you have to remember a lot of native data frame operations happen column by column by column. So that's one of those foundational things we need to think of. So we can add two columns together and store the results in a third. So I create this data frame with columns A and B, and then I create column C that's just A plus B. That doesn't work. Column C is just equal to A plus B. And it's really hard to see, but there are results right there, 6, 7, and 8. Or 5, 7, 9, sorry. So we've talked a lot about scalars and vectors. Why this is important is when we talk about vectorized operations. And this is really the key to understanding how pandas works and how to be efficient in pandas. You need to think about passing the entire vector, the entire column, or the entire row to an operation, rather than operating on data one element at a time. So in standard Python, if we have a collection of data, we usually loop through it. So we've got a list and we say, for each element in the list, do something to that element. And that kind of looks like this, right? We take our list, we take each element, we pass it to a function, we get the result. So you see, we have to go through the logic of iterating. We have to call the method multiple times, and then we have to get the data back from the method. Those are very expensive operations when it comes to code. So if you're doing a short list, that may not matter. If you're iterating over, I don't know, 1 million columns or 1 million points of data, that's going to take a long time, relatively speaking. So a vectorized operation takes that whole collection of data, that whole vector, and passes that to the function. So the numpy.square root function will take the square root of every element in that list you passed. So 1, 1.4, 1.7. And we can do the same thing to a series. We can pass that series, or we can pass square root to the series, and it will operate on that whole series. So again, what this looks like is just we're passing that entire vector to the function and getting that back. We've only got a single function call. We're not worrying about iteration. This is going to go a lot faster. Like I mentioned, those for loops are very expensive, and the processor has special hardware to accelerate and parallelize operations if it can. A lot of these functions that are written to be vectorized can take advantage of that. But just pure Python, a for loop, it can't really know what's going to come next, and so it can't optimize that nearly as well. So that's the background of why these vectorized functions are important. So again, you're going to take all your data points, pass them together. You're not operating one by one. You're going to do everything all at once. So you're sending a set of data, not an individual point. I'm harping on this, but this is kind of the key point of pandas. This is what took me a while to wrap my head around, so I really want to get this kind of imprinted in your brains. So let's look at an example. We're going to load a data frame here. We're going to take our SGID county boundaries. I downloaded them to a geodatabase. We're going to load that in. We're using the ArcGIS API for Python's spatially enabled data frames to give us access to be able to read feature classes here. And we're just going to kind of print it out. And you can see here we've got a series of columns, and we got a bunch of rows, and that's all the data. And I'm using .head to just show the first five rows, but there's 29 different rows because there's 29 counties. So you can see it's a table. It's a spreadsheet in code. That's really what we're working with here. So like I said, it has rows and columns, and those there is an index for all the columns and an index for all the rows. The columns is just called columns, while the rows is called the index of the data frame. So there's index with a big I, which is all the rows, and then there's index with a little I, which is just the collection of labels for either the rows or the columns. That can be a little confusing, but hopefully it'll become clear as we go along and as you play with it a little bit more. So if I look at the data frame index, you can see there are all the labels that I've set up for every row. Those are the FIPS codes for every county. I can look at the columns, and that's the list of column names. So that's what we'd call the fields in feature class. And we can think of and extract every individual row or every individual column in a data frame as an individual series. And I'll explain this notation a little bit later, but here you can see I'm getting the name column for all the counties, and you can see the first 5, Cache, Duchesne, Davis, Millard, and Wasatch. Likewise, we can do it for every row, and here is the first row, all the columns. We've got our object ID, we've got our county number, entity number, whatever the heck that is. We got our name, all the different columns associated with that row.
Jake, question for you.
Yeah.
If you go back one slide, what does a colon do in these calls?
We'll get there just a little bit later, because there's a whole set of syntax for accessing this. I'll explain that here in a sec, okay? Okay. Before we dive into that, though, I want to hit data types really quick. Pandas uses NumPy data types under the hood. So normal Python, you have like string or str or int or float. Pandas uses things like NumPy. So you'll see int64, that's a NumPy 64-bit integer. You'll see float64, which is you'd call it a double in Esri speak, a double precision floating point number. Now these are interesting though here. Object, that basically means it stores a unknown or any sort of Python object. So if you have a column that has multiple types, so you've got some strings and some ints and some floats, the data type for that column is going to be object. And then if you try and do a string operation on that, it's going to throw up an error like, hey, I don't know how to split the integer 45 on a column. You're trying to split a string, but it's a number, it just doesn't work. So that's something you want to be aware of. And a lot of your time in Pandas will be spent cleaning up your data, getting it to the proper data type so you can operate on it. So again, strings are a special case. Strings by default use that same object data type. So if you look here, I've got a mixed one. I've got a string, I've got an int and a float, and that's getting cast to object. There are ways around that, though, that I'll handle when we talk about handling missing data. Because, as everybody knows, not every data set comes with nice, clean data. Not every row has a value for every column. So how does Pandas handle that? So you see, I'm going to build another data frame here with none in both an int and a string. And you'll see it for the integer, it uses np.nan. But wait, those are integers, but that data type is a float. What happened? Well, default NumPy integers have no concept of null, of not a number. Every integer by default has a value. And so it casts the whole thing to float, to a decimal number, and then uses the decimal np.nan, not a number, to capture that. But you can see in the string, because it's objects, it's just using the pandas none object. This can be kind of annoying when your floats turn into strings, or your integers turn into floats. If you've ever uploaded data ArcGIS Online for a web map, and it's nice integer-based data, and then you go to create your pop-up, and suddenly it's got 6 zeros after the decimal, you're like, what the heck happened? Same idea here. So Pandas has introduced these nullable data types, and we can use the .convertDtypes method to convert the entire data frame to these nullable types that have native support for missing data, for missing values, and kind of handle that directly. So something I should mention, I've been using the .info method here to explain, to kind of take a look at the data frame, what's going on. So that gives us kind of a printout of the column, column name, how many non-null values there are, and the D type. Now, we converted that same data frame from before that had 1.0, 2.0, and NaN and now it has 1, 2, and NA. It's back to an integer, but note that it's capital INT, not, if you look earlier, not lowercase int. The capital is the native pandas nullable data type. So it's a little bit tricky, and again, there's a whole documentation explaining this on the pandas website, so you can really dive in. But I want to make you aware this can be a great way if you're running into null values to dive in and really figure out what's going on there. You also note that our object got converted to a string. And this is a little bit more performant. You don't have this, okay, it's object. Is it all string? Is it strings, floats, and booleans? You know, it really cleans up your data. So like I said, you're going to spend a lot of time in pandas cleaning data. So now to get to Matthew's question here, the brackets, the colons, how do we reference individual columns, individual rows, or individual elements within it? So we're going to use the data frame bracket notation a lot. This is a lot of text. Take a picture if you want. Go download the slide. Read it later. We're going to go into this in detail. But basically, there's 4 different things you can use those brackets for. The first one, if you just pass a single string, it will give you that column as a series. We've been doing this before, but I'm just taking the name column of my county's data frame, and it prints it out. So again, that's just the names. And that's a series, or a panda series. If I pass it a list of strings, so the inner brackets denote the list, and then I pass that into the outer brackets for the data frame, and that gives me a new data frame of just those columns in the in our original data frame. Now I said new data frame. It's actually a little fuzzy. Sometimes it gives you a copy. Sometimes it just gives you a view into the original data frame. And this is going to come up again a little bit later, and it may trip you up a little bit. So just kind of setting the table there. Now to get to Matthew's point, what about the colon? Well, if we do a series of integers with a colon, it acts just like normal pandas slicing. If you've ever sliced a list or sliced a string, same idea. So we're passing 3 to 5, we get 2 values right there. So the fourth one, this is where it gets fun. This is where you kind of have to wrap your head around what's happening. But if you pass it a series of booleans, it will only return the rows where that series was true. So I'm just taking the first 5 rows and making a copy of it. So we're just working on the first 5 rows of our data frame. So I'm going to pass it this list of booleans, true, false, true, true, false. So that's just going to return 3 rows because there's 3 trues in there. And it returns the rows according to their position in the list. So that's great, but why would you ever pass a list of true, false, that's kind of painful and annoying to come up with that. Well, we can create that list programmatically and pass that. So we want to filter out all our counties and filter down to just the counties with a population greater than 100,000. So I'm going to use that single value to create a series of just that last census population and create that series. So we've got 5 values, some greater, some less than. I'm now going to create a new series based on this Boolean comparison to say whichever of these values is greater than 100,000, and you see here is our Boolean series. True, false, false. And now I'm going to pass that series back into the indexer, and you can see I just got the 2 rows whose population last census is greater than 100,000. You're going to see that, sorry, let me back up. So we did that in a couple of different steps, but what you're going to see a lot in example code is people doing that all at once. So here, in my head, I think of this as where. like a SQL or a definition query. It's probably not entirely accurate. You probably get in trouble by thinking of that, but I think of this as head DF, where head DF pop last census is greater than 100,000. So here's our comparison. Here's our comparison. That creates a series of true, false, true, true, false, or whatever. And then we pass that into these brackets to pass that series of Booleans into our original data frame, and we just get those two lines. This is how you're going to go in. You're going to use this a lot to filter down your data, to look at just a subset of your data, and you're going to see this all over in examples, Stack Overflow. This is very popular, so this is something that you'll really want to get familiar with. And again, you can go download the code, really look into it, play around, see what's going on. Now, we can also use .isin to create that same or a similar list of Booleans. So I'm saying where that color 4 column is in 2 or 3. So that's saying I want all rows where color 4 is either 2 or 3. And if we come over here and look at color 4, 2, 3, 3, 2, the 5th row, whichever it was, I think had a value of 4. So we didn't include that. And so there are several other methods you can use that return a Boolean series, and you can use those to really filter down your data set. And again, you can see isIn just returns true, false, true, true, false. We pass it in, and we get just those rows. So now we want to get at individual rows, individual columns, and individual values within those. And we're going to use .loc and .iloc. I love programming, saying programming terms out loud. They make total sense in your head. You say it out loud, you're like, .loc. That just sounds weird. But hey, we're programmers. So .loc gives you label-based access to your data, to your rows and your columns. So here, single value, we're getting an index label. So this is a little bit different than before, where we didn't use .loc. That would have given us a column. This is giving us a row, but we're passing in the row label, and we're getting all the data for that row back. If I pass, note that this is not a list. We're just passing basically 2 arguments, 2 parameters to .iloc, but we're still using brackets instead of the common parentheses. So I'm saying, for row 49051, give me name. So the name of that row is Wasatch, and I've just accessed a single element in my data frame. Now, finally, we're going to get to your colon there. We can use the the Python everything slice. So in Python, we use slicing. If you just use the colon without a beginning or an end, it just sends everything. To get either all the rows or all the columns based on the position. So we want all the rows, we want the name column, and there we go. Now you'll notice that this is very similar to what we did before. It's the same output without using .loc, just using standalone brackets. Pandas sometimes violates the Python principle of there should only be one way to do it, and it should be obvious. You're going to see as you dive in, sometimes there's multiple ways to get what you want. It can be a little confusing, so that's why we're really going into in depth here to figure out all these different things so that you can think, when you're programming, why is this not working? Oh, I remember him saying something about the different ways to access. You can go back and figure it out. So just as we could pass a list to the normal, we can pass a list to .loc. So I'm saying all the rows, give me the name, and pop last census columns. So again, here we get a data frame with just those things. It really makes it easy to subset your data and not worry about all these different rows, because who's ever had a feature class with 25 different columns and you keep having to scroll over, it's a pain in the butt. You keep forgetting where you're at. This gives you really good access straight there.
Did you define that FIPS number as the index at some
I
point?
did, yeah.
I didn't do that. like automatic.
Correct. When you load a data frame automatically, it usually just gives you a range index, 0, 1, 2, 3, 4. I defined that when we loaded it in to give us some easier indices to remember, right? Because give me the first row. Well, that's row index 0. It just blows your brain, right? There's, what's the joke? Programmers can there are two common errors in programming: misnamed variables, missing documentation, and off by one errors. This is an off by one error. So we passed a list of columns, so we get multiple columns. In this case, we're passing a list of rows, and all the columns to just get those all the data for those two rows. So multiple ways of doing it. Now, in comparison to .loc, which uses which uses labels, .iloc uses index. So this is index location. And this, again, right here, now you have to think, give me the 0th row and the 5th column, which is actually index 6 or index 4, off by 1. This is really useful if you know I want the first row, I want the last row. So iloc 0. You can see our index name was actually 49005, but index 0. Same with columns. Give me the first 5 rows and the first column. You'll see that that's kind of like doing that head call, but in a less readable way. Frequently, you'll use indices if you're like, oh, I know that I want the last row or the last 10 rows or whatever. That's when you'll use this the most. Now, this is something I ran into a lot when I was first doing Python, because now we know how to get our individual data, and we're going to want to start operating on it. But chances are you're going to run into this error, setting with copy warning. And you're being like, what the heck does that mean? So to kind of demonstrate this, I made a copy of our data frame so that I don't mess it up. Call it testdf. I'm going to say I want all the counties that are in State Plain Central, and then I'm going to take the foo column, right? In this case, I'm going to create the foo column. If you reference a column that doesn't exist and assign to it, it'll actually create that column. You don't have to, and this is what makes it really great against ArcPy, you don't have to go in and add field management and then go through all that hassle just to add a column. You just reference that column and assign a value. It's really easy. So I'm going to make all rows have the value of 3. And it throws this warning. A value is trying to be set on a copy of a slice from a data frame. Well, what does that mean? Well, we're kind of chaining this operation. We're saying, do that Boolean index, which returns a view, doesn't return a copy, it returns a view of our data frame. Then we're going to modify it by creating this column and setting it to 3. It's saying, whoa, heads up, you're modifying your original data frame. And that could cause so many problems down the road that we're not actually going to do it. We're going to raise a warning. So if you come and look at our data frame, we don't have the foo column here. It said, nope, not going to do it. So how do we get around this? We got 2 options. The first one, like it suggests, is to use .loc instead. So for the rows, I'm passing our same Boolean index, saying, give me all the rows where the state plane column is equal to central. And then for the foo column, assign it to 3. So this is all happening within a single call, and we're assigning that value. So now if you look, there's our foo column, and we've got the value of 3 in those ones where the state plane was central. You'll see there's 2 here that is north, and it says, oh, nope, you didn't assign to that, so I'm just going to give it the default value of nothing. And again, it's casting our insta floats because I'm not using the special null type or nullable data types, so I have to remember this is now a float column, not an integer column. The second one, and I use this a lot when I'm trying to subset data and only work on the subset, is I'm just going to create a copy, explicitly create a copy of the data set. So there's my Boolean index, say, give me all the rows where a state plane is central, but now copy. And so instead of returning a view, I'm getting a view and I'm taking a copy of that view and storing it into a new place in memory. So now I've got my original data frame, I've got my new subsetted data frame, and now I can operate on that subset without ever touching the original. It's not going to throw any warnings. And again, I'm using head to just show the first 5. You'll see they all are foo and they are all state plane central. So again, I use this very frequently to subset data down that I want to operate on. This is your definition query in pandas.
Does that copy only include the ones that you selected there?
Correct. Yeah. Because this only returns the view that meets that criteria. Okay, so now that we've figured out how to look at our data, now we want to operate on it. So let's talk about working with columns. And again, pandas, every column is its own collection, its own vector, its own series. And so a lot of operations can just be called directly on the columns. So again, I'm going to create a copy of our data frame to operate on. I'm going to call it density. And I'm going to create a new column. I want to figure out the population density. To do that, I need to get the area from the geometry column. And I'm using some stuff here we're going to touch on later to get that area property and convert it to square kilometers. But now I'm just going to say, take my population column, divide it by my area column, and save it in my density column. So no add field management, no field calculator. It's all just right there, one line of code. Divide this column by that column, store it in that column. You can see there's our area column and there's our density column.
That only happens in memory, not on the original.
Correct. So this is all in memory. And as we operate, we'll do a bunch of stuff in memory, and then when we're done, we'll write it back to disk.
So when you add the column, will that physically add that field to the data, to the feature class?
Not yet, because we're still operating in memory.
Okay.
And so when we're done, we're going to do a bunch of different operations, and when we're done, we'll write it all out to a new feature class or overwrite the existing one, and now it will be an extra field.
Okay, so when I do the add field management, it actually adds that column to the feature class, but this doesn't.
Yeah, this just does it in memory. Your feature class on disk is still whatever it was before you read it in. And then this just, when you're done, you'll write it back to disk.
Okay.
So, and this really speeds it up because adding, add field management, you have to, it opens the feature class, does the stuff, saves it, closes it. It takes a lot longer than it should. And this makes working with columns really easier, which we'll see more here in a second.
Could you also do kind of like ArcPy functions, like find the X and Y centroids and add those as?
Yes.
Yeah.
There are ways to go from a spatially enabled data frame to an ArcPy feature collection, which you can then pass into ArcPy things if there's something that you absolutely must do in ArcPy. Centroids is one. You can get centroids from a data frame. The spatial methods give you that. But ArcPy, you can't constrain it to be inside the polygon, right? Like in ArcPy, you say, give me the centroid, make sure it's within the polygon. Spatially enabled data frames don't give you that. So I've had times where I've had to go outside to ArcPy to do that and then pull it back in.
Okay.
So you can round trip it, but it's a little painful.
I was just going to add one thing. At the UC last year, so right now you can't operate on spatially enabled data frames with ArcPy functions or geoprocessing tools. But at the UC, they said that was something they were looking at adding in the future. So you could potentially run ArcPy tools directly on these spatially enabled data frames.
That's good to know. Yes. Yeah. We're using spatially enabled data frames from Esri. There's GeoPandas, which is similar to that, gives you a lot of spatial operations, spatial tools. Very powerful. So if you're wanting to go the open source route, a lot of what I show here with spatially enabled data frames can be done with GeoPandas data frames as well. So renaming and reordering columns in ArcPy is a pain. You've got to set up your field maps and everything. Well, I don't like density. Let's name it something a little bit more creative. Or pop last census. Well, when was the last census? Let's say it was 2020. So I'm just going to call rename with this dictionary. Columns equals, and this is the existing name, and this is the new name. And you can see my pop last census column is now pop 2020, and my density column is population per square kilometer. Real easy, one line of code. No shuffling through, no creating intermediate feature classes. It's all right there. What if we want to move columns around? You add a column, it's way over at the end, but you really want it right there towards the column that it was created from. We can just call .reindex and pass a list. And it will include those columns in that order and just those columns. So this is also a really easy way to kind of subset your data down. You load in a bunch of data, but there's a lot of data there that you don't really care about, a lot of columns that you don't need for this operation. Let's just get rid of them. And so you can see now I've just got these 4 columns, my created one, the name, the entity year, and the state plane. Now, another way to delete an individual column is just call the Python delete method on that column. So delete state plane, and you can see this happens in place. So we're not creating something new, it's just modifying our data frame. And you can see state plane is no longer there. There's also the .drop method, which rather than operating in place, returns a new data frame. So now I'm going to drop name, and I'm going to use axis columns. I'll explain that here in a second. And I'm not assigning this to anything. It's just returning this data frame, which the notebook is printing out for us. So I'm doing this operation, but because I'm not assigning it, it just kind of, the result just disappears. It gets garbage collected. And like you've seen before, I can update all the values in a single column just with this simple assignment. So no field calculator to do all the values on a single column. Is just right there. And again, there's that .info method that I explained earlier. You can see our population is a float, name is a string, which in this case is an object, and my entity year is an int. So let's talk about working with strings, because a lot of time you're working with data that comes in as text. We can use the .str attribute of a series to access most of the common Python string methods that will operate in a vectorized format on that method. So my county names were all caps and it was just the county name. I want something a little more human readable, so I'm going to take that column, call .string.title to title case it, and then add space county, and now my name column is a very human readable, easy to understand format. And that's all using .str. Now, frequently you want to split a string. And this gets a little difficult if you don't understand what's going on. So we're going to call str.split, but now I just want the first thing in that, the 0th thing. So let's say my data was this, and I just want the county name. I don't want county associated with it. So I'm going to split it, and by default, split operates on white space. And then I'm going to call str bracket 0 to get the 0th item in the resulting list that you get from splitting. And again, I'm just going to call head to show the first 5. So there, I've taken my cache county, stripped off the space county, and just got the name. So to really show you how this can get complex, this was something I was working on just last week. we have a CSV of school names and addresses. We want to geocode the addresses with the UGIC API client, but the address is all in a single field, and we need a street address and either a city or a zip code column. Now that street address, or the address column, uses two different ways to split, or is formatted two different ways. Sometimes it's two lines, like 123 South Main Street, Salt Lake City, Utah, and there's a new line character there. Other times it's 123 Main Street, comma, Salt Lake City, comma, UT, zip code. So we need to figure out how to split all that up. So this is how you read a CSV into pandas. pd.readCSV, and you pass it the path to the CSV. And then I'm just going to rename the columns to be a little bit more human readable. And you'll note here what I'm using is called chained operations. This returns a data frame. And because it returns a data frame, I can then call rename on that directly to then call rename on that return data frame without having to do two different things and assign that a temporary name. It's all right there. So you can see here, let's look at this one. You can see we've got a new line character in there to split up our names, but in this one, we've got a comma. So we need to figure out how to work through that. Again, you'll want to download this to really dig into it, but I'm going to use string.contains, and I'm going to pass it the new line character, because that's literally in the string. I'm going to create a copy. So I'm saying just get the rows that have the new line in it. Then I'm going to print the length, so you can see we've got 49 rows out of the original 83. So now we're going to split on the new line, and then some of these have a kind of a secondary street name in parentheses, and that's going to throw off the geocoder. So we want to strip that out as well. So we're going to split on the new line, and then we're going to split on the parenthesis, and then we're going to strip off any white space, all in one line. So we split on the new line, we get the first element of that split, and then we're going to split it again on an open parenthesis. We're going to get the first element from that, and then we're going to strip off white space. And you can see it takes that. Let's look at one that has, so 5205 South Holiday Boulevard, parenthesis 26 East, new line Holiday. And that strips it down to just that one street, so we can then pass that into geocoders. So you can see pandas can give you a lot of power to clean up your data in just a few lines of code. Again, download this, look at it, really dive in to understand what's going on. Now, we've done that for the ones that have new lines, but what about commas? Well, I'm going to select, but in this case, I'm going to negate. So give me everything that contains it, and then invert. What was true becomes false, what was false becomes true. And in Python, use the exclamation mark to invert. But in pandas, use the tilde. So the tilde in pandas is the negate operator, and then I'm throwing everything I want to negate into parentheses just to be very explicit. This is what I'm negating. Sometimes you can leave it out, or you can not include the parentheses. In this case, I probably could get rid of the parentheses, but if you're using a complex statement in here that includes ands or ors or stuff like that, you'll have to wrap it all in parentheses. So we got 35 rows, and then this split is much simpler. We just need to split on the comma. So we split on the comma, get the 0th element, and here you can see now we've got all our strings. Finally, we need a new column that includes the zip code. Fortunately, this is very simple because the zip code is just the last element in every one. So I'm going to combine everything together, and we'll talk on this later. And then I'm just going to take that address column, I'm going to split on a blank space, and instead of getting the first element, I'm going to get the last element, and save it to our zip column. So we've got our street address, we've got our zip, and now I'm ready to pass this into our geocoder with just those columns, and it's all right there. Now we're going to write our data out to CSV. So we just take our data frame and we call the .toCSV method, and we pass it the path that we want to save it. So it's going to be very similar to save feature classes out. We're going to call .spatial.toFeature class and pass the path that we want to store our data in. So that's how you read data into pandas and pull it out or save it, as well as do a bunch of string operations on it.
Is that, when you do the combine, is that what the file would be named?
Yes, yeah. So that's the file name. And if you're doing a geodatabase, it would be so like data.gdb/feature class name with no trailing extension, just like ArcPy. Okay, we've been going for about 45 minutes now. I'm going to say, let's stand up, take a 2-minute breather, because nobody likes to sit for 90 minutes straight. So we'll take 2 minutes. Now's your chance to leave without offending. Yep.
On that last one, maybe it's a dumb question, but your -1, so like where you call it 0, right? First reaction.
Yep.
This time you call it -1. How do you know
Yeah.
which one to use as far as the server?
So this, in this case, the data is telling you, right? I knew that, so this address right here, if I'm splitting on this new line character, I know that the split method will return a list of all the elements in between those new lines. And I know that in this case, I just want whatever comes before the very first one. So that's always going to be the first element of that list that split returns. So the data told me, give me the first element. For the zip code, I know that the zip code is always going to be the last. If I split by the space, it's always going to be the last element. And so that's just something the data is going to tell you. If you need to get more complex, you can use regular expressions to pull out patterns. Eric's done a lot with regular expressions. If you were at his presentation yesterday about the UDOT parcels, so a lot of power there. Regular expressions are really powerful, and they will give you the biggest headache of your life. So
Yeah, I was using them, and then I found your address parser. It's like, this is so much better.
Yeah.
Yeah.
So
So the -1 always just selects the last element. Is that what it does? Like that into
if you don't provide the .str.bracket, it will actually return the whole list. So suddenly your data frame contains a list where you're expecting a string. Because it can store any Python object. So. Okay, let's dive back in. Chances are we won't cover everything that are here in the slides, so again, that's why I'm saying go download them. I've tried to comment them fairly well. So we've worked with columns. Now we need to talk about working with rows. And this is where we're going to get back into that vectorized, pass all the data in all at once sort of thought. So I'm going to start off with the wrong way to get row values. If you're coming from cursors, if you're coming from any sort of default Python programming, you're going to think, oh, I'm going to iterate through the rows, and then I can iterate through the values in each row. So if you absolutely have to do that, you can use .itertuples, which will return a tuple for every row. It's actually a named tuple, and then you can access the columns using .column name. So in this case, I want all counties with population over 200,000. I iterate through the rows. If that's greater than 200,000, print the .fips column value. We're only iterating over 29, so the speed difference really doesn't matter. But again, once you get into 1,000 records or 1,000,000 records, the speed differences are going to be ginormous. So this is how you absolutely have to do it. Don't do it this way. This is the wrong way. So iterating over the rows is kind of like using a pair of pliers to pound a nail. You can do it. It'll work. People are going to look at you funny. We're changing our thought process. Rather than iterating over rows, iterating over columns, we're going to pass an entire set of rows or an entire set of columns to the function. Ultimately, this is going to be a little bit more readable because you're not saying for I in rows, for j in columns, if it's 3, 4, do this. That just isn't readable. Trust me, I've done it. So, for example, again, we just want that 200,000. I'm going to say, give me the FIPS column for anything that is greater than 200,000 and cast that to a list. And we're going to see some more examples here in a minute. So rather than iterating through, we're going to use the dot apply method of a data frame. So dot apply will perform any arbitrary function, any function that you pass it, to every value in the data frame, either working row by row or column by column. So again, instead of passing individual elements, we're passing a whole function to the collection of elements. So if we call it on a series, it sends just that series to the function. If we call it on a data frame, it's going to send either every row or every column to that series. The functions that we pass can be of two types. It can be an aggregate function, which says, take all the data and give me a kind of single number, single value that's based on all that data. Or it can be a transformation function, which says, take every value that we pass and do something with it and then return a new value for every one. So let's look at some examples here. We're going to just get the population columns from our county's data frame and save it to a new data frame. So we've just got two numeric columns to work on here. So let's talk about aggregation. Again, it takes the input data and kind of aggregates it into a single value. This is usually going to have one dimension less than the input data. So if you pass a data frame that has rows and columns or multiple series, it's now just going to give you a single series. If you pass it a series, it's just going to give you a single number, a scalar. So let's take the average values in one of our columns, or of each of our columns. So we're calling it on a data frame, we're passing mean, so the average value of the last census column is 112, the average value of the current is 116. So you can see we've got our average population of the counties in Utah, just like that. But what if I wanted the average of those two columns for every row? Well, now I'm going to change axis equals columns. The default here is axis equals rows, so I didn't include it. But by axis equals columns, it's saying pass each column to the data frame or to the function instead of each row. So this is a little confusing. Let's look at it visually here. So with axis equals rows, we're saying take this column and operate that function on every row in that column. So we call numpy.mean on 14710, and we store that in a new series with index foo, single value in that series. And then we operate on this column and this column. So even though it's axis rows, we're operating column by column because we're operating on each row in that column. Likewise, with columns, we are passing each row to our function, but we're operating on each column in that row. This took me a while to wrap my head around, so that's why I did this visually, so I could say, okay, what's actually happening here? This is fairly simple with some of these mathematical functions where you're just passing a single mathematical function, but you don't have to just pass predefined. You can define your own function here. So you can do whatever the heck you want to individual rows or individual columns, and this really helps me keep it straight in my head. So let's talk about some transformation operation instead. Now remember, we're returning a new value for every value in the original data set. So let's just take square roots. So I'm going to take our data frame, I'm going to apply square root. This makes no sense for population, but this is the data I'm using, so bear with me. The square root of the census population for 4905 for Cache County is 364.9. So there are 340 square people? I don't know. What's a square person? But the idea here, again, is this data frame is the exact same shape as our original data frame. And you can see we're taking this, if we can pass axis equals columns or axis equals rows, but it really doesn't make a difference because we're passing that data in and it's just returning a value for every one. So this example shows passing axis equals columns. If we did rows, it would just take that data, and put it there. It may be a little bit more performant to operate column by column instead of row by row, which is probably why it's the default. Now, for performing arbitrary functions, we can use lambda functions. Is anyone here familiar with lambda functions? Anybody seen these before? Okay, a handful. I'm going to go in depth for those who haven't seen them because you'll see this again on Stack Overflow. You'll see this in examples. I really want you to kind of lay the groundwork here so you know what's going on when you see it. So lambda functions are small one-line functions that you can define without using the normal def, function name, argument list, and then a whole bunch of code. They're useful for creating small bits of code that you can then pass as a function object to another function. Why you'd want to do this is apply takes a function object. We're not calling the function we're not saying function and then passing the parameter, the series as parameter to that function. We're taking the series and passing the function to that parameter. So, for example, we could define our get square kilometers function. We pass it a geometry object and we return geometry area divided by 100,000. And then we pass that with apply to our shape field. This is how we get the area from our earlier example. But hey, we've got 2-3 lines of code there, and that might affect readability. There's more code to read, there's more code to debug. We want to be concise. Well, instead, we can just use a lambda function. We're going to say lambda x dot area divided by 1, or I guess that's 1 million, and we're just going to pass that to the apply function. So why does it look like that? What does all that mean? So what's the syntax? So lambda functions are defined with the statement lambda, and then the name of the variable for what's being passed in, colon, and then the operations that you're going to perform on that variable. So variable name can be anything you want. X is very commonly used in examples because it's just, in math, find X, right? So that's what people think. But it can be whatever you want. Again, readability matters. So if it helps you remember what you're doing, by all means, use a different name. I very frequently use this to do write custom code that operates on a row by row and gives me access to the columns in that row. So rather than X, I'll say row, and then I can access the individual columns in that row. Again, everything after the colon is whatever you want to do with that. And Normally in a Python function definition, we manually say return, whatever we did. Lambdas have an implicit return. Everything in that, let's see. So this is our lambda function here. So lambda row equals, or lambda row colon, then I'm going to take row pop last census plus row pop current estimate, divide by 2, and that gets, that is the implicit, it implicitly returns whatever the result of this is. And I'm passing this function using access columns so that I'm doing it to every row, and that then applies that new custom function to every row in the column, or every row in the data frame. And so basically what I'm doing here is I'm taking the average of those two rows. Again, contrived example, but you can see how I'm using lambda functions to access the individual columns in every row. So if you're thinking of you've got a process where you need to do something a little bit more complicated using multiple columns for every row, you're not going to use iter tuples to iterate over every row. You're going to use dot apply, and you're going to pass a function. So now we're going to go one level deeper. This is Alice in Wonderland. This is Inception. We're just going to keep going one level deeper. We're going to use group by now. Now, group by is a very powerful tool to perform the same operation on group your data into multiple groups and perform the same operation on that group. This is like doing a definition query, performing an operation, saving that out, then changing the definition query, performing the same operation, save that out, change your definition query, etc. This just separates your data using something in your data and then applies that same operation. So it splits the data frame by the values of the function, applies a function, and then combines the data back together. So split, apply, combine. So I'm going to group by the state plane, and I'm going to take the average of the last census population and return that based on state planes. So now I've said, you can see, okay, south, average population of the counties there is 35,000. It's very heavily weighted by Washington County, otherwise it would probably be in the thousands. Whereas central, this includes Salt Lake and Utah County. I think it includes Davis as well, much larger. So really quick and easy way to get some summary data about your whole data set based on a category. You can think of this as we symbolize by unique values when we're mapping, right? So we go symbolize by unique values, choose our field to get our unique values, and then base our symbology off that. This is the data equivalent of that operation. We're operating based on unique values. So what's happening? Well, we're taking our data frame, we're grouping by the group column, we're operating on the foo column to get the mean. So we're breaking our data frame into two sub-data frames, or two groups. Each one is its own data frame. So internally, we now have two data frames, and whatever operation we can perform on a data frame, we can perform on each group. So in the split, we're splitting into the two data frames, and we're going to apply that function, the average function, to the foo column. So taking the average of 1 and 3, and we're going to combine that that just gives a single value. And because we're combining two single values, we get a series out. So we're splitting it, we're applying our function, and then we're combining. Again, each group by group is its own data frame. And we can look at the group by object to kind of investigate those a little bit. So I'm just going to group by state plane and save this to what I'm calling group. This is a group by object. We can look at the groups. we get a dictionary where the key is the unique value, and the value is the list of row indices. So we can see central, north, south. We can look at an individual group. So we call .get group south, and you can see that group is just a data frame. So really what I'm trying to impress upon you here is that group by creates new data frames for each group, but behind the scenes. You don't have to save them. You don't have to definition query out, save it as its own data frame, operate, do all this. Group by handles the splitting and the recombining for you so that you can focus on the operation itself. And again, where we used apply before to do any arbitrary function that we wanted, we can use that here with group by and the data frames it creates. How it combines those is going to be a little bit different, so we're going to go into some detail here. If you use a transformation function, remember this is a function that returns a new value for every original value, it just operates on that sub-data frame and then combines them all together as a single data frame. So this can be useful if you want to maybe apply the same correction factor to every value within a group, but a different correction value between groups, or compare the value in each group to the group mean. Again, it's a bit of a contrived example here, but I'm going to take I'm going to create this new data frame with just these columns. I'm going to group by the state plane, and I'm going to apply this function that says take the value, divide it by the sum of all the values within that group, and return that. So this gives me the percentage of each county's population for that state plane group instead of that percentage of the population, the county's population to the state as a whole. Now it doesn't break that out so you can see the state plane here, but these numbers are now percentage of the group's population rather than percentage of the whole population. So that's a transformation function. What if you use an aggregation function that returns a series for the whole data frame? It then takes those series and concats them into a new data frame based on the function name, or excuse me, the column name. So if you want to run the same operation on multiple columns, like a descriptive statistic, this can be useful. So I'm going to, again, group by state plane. I'm going to pass our two population columns, and I'm going to apply the mean. So you can see our average population for the central was whatever that is, and the current estimate. So we're applying a descriptive statistic per group across the whole data frame. Finally, if we're using an aggregation value that returns a single value, it's going to just recombine them into a single series. So if you wanted to get a total value for every group, like summing the populations, we can just say group by state plane, take our last census, give us the sum, and there you can see the total population of each of those state plane groups. So it may seem a little trivial that we're diving into this, but again, I want to lay the foundation. I want to put this bee in your ear, this bug in your mind, say, oh, state, group by is really bothering me. Why is this combining weird? Oh, wait, he talked about this. Let's go back and review. Again, this is one of those things that I spent a long time figuring out, so passing my knowledge on to you. We're going to go into an example here. I'm going to go over this quickly. Again, download the code, look at it, really parse it. But the FCC has released the new broadband data that they've been collecting by point rather than by polygon. But this is based off of individual broadband serviceable locations, or BSLs. While we can't get like a lat long value for every BSL unless we sign a big license with the FCC, we can get the availability data for every location ID just from broadbandmap.gov. You can go download the data. So I've already downloaded the data for all of Utah. And this comes by technology. So I downloaded all the DSL data, all the cable data, fiber, wireless, all this into individual CSVs. Now, the FCC, or a different agency for funding, says we only want to look at a certain subset of technologies to see if their speeds, if their advertised speeds meet a certain threshold. So I'm going to take this data and figure out, based on the technology type and the speeds it gives, whether each point has we're going to call it served or unserved, served, underserved, or unserved, based on certain speed tiers. So that's a brief overview. So to dive into this code, I'm going to take the path of the folder, and I'm going to use the .glob method, the wildcard method, to get all the CSVs, a list of all the CSVs in that directory. Now, for every path in that list, I need to get the technology name. And so I'm going to split on the underscore, and then I'm going to read that CSV into a data frame. I'm going to assign that technology to a new column so that I have a human readable way to know what technology I'm dealing with. And then I'm going to append that to this list of data frames. And then I am combining all those individual data frames into one big data frame. So now I've got one huge data frame with multiple rows per location ID. And I'm just going to take value counts, and this is a quick way to look at, how many rows do I have that, or how many of each unique value are there in a row, or are there in the data frame. So I've got 2.9 million rows that provide satellite data, 1.65 that's fixed wireless, but only, 570,000 that provide fiber. So, quick way to look at your data. So, this is Harry. Download it later, look at it. But these are my Boolean conditions. I'm saying where the speed is greater than 100,000, or greater than 100, or less than, or greater than equal to 20. So, 100 down, 20 up is my top tier, and then I've got a middle tier and a bottom tier. And I'm using this np.select. And that basically says I've got these series of conditions. There's one condition, there is two condition, and there is condition 3. And whatever rows meet condition 1, get this value. Whatever rows meet condition 2, get this value. Whatever rows meet condition 3, get this value. And then if they don't meet any of the conditions, I'm just going to use this default value of NA. So you can go dig into this later to figure out exactly what's going on, but I'm basically assigning values based on conditions. And then I'm going to group by location ID because I've got multiple rows for every location ID. I want to focus on each location ID. So, and I'm just going to get an example one so you can see here. I've got the technology name, so this particular point has a lot of options. It's got cable, copper, which is DSL, fiber, couple satellite, couple wireless, another satellite, with varying speed classifications. We've got some that are above 120, some that are under 25.3. So, basic point here, we've got multiple rows for each location ID that have different technologies, different classifications. So here is the function that I'm going to apply. I'm going to say, if my classification is greater than 120, I want just to return served. If it's between 120 and 25.3, I want to return underserved. And if it's under 25.3, I want to return unserved. So I'm taking in a row and I'm performing an operation based on the values from that row. Now, again, we only wanted to look at a specific subset of columns in there: cable, copper, fiber, licensed wireless. So I'm going to use a Boolean index using the .isin to just filter out my data frame to just those columns. And and then I'm going to group by location ID, and I'm going to pass my function to that group by, and because that returns a single value for a series, the result is a series just with served, served, underserved, served. So now I have a single value for every unique location ID within that data frame that I can then map, pass to the broadband office, say, these are the areas to look at. So I've taken a bunch of data, done some pretty complex operations, and gotten a single value for every item. So this is how group by can be very, very powerful, allow you to look at your data, subset it down, and perform an operation. Okay, 10 minutes. We're going to go fast. I've been using the pd.concat pretty frequently, but basically all this does is useful for adding rows and columns to your data frame. It's taking either a row and adding it to the bottom, or a column and adding it to the left. So we're going to create a new data frame. We want to add another row. We make sure that the schema is the same, and we combine it, and we see our new row is just tacked onto the bottom of the data frame. We want to add some columns. So I say, let's create a new status column, and these are the values for every row, a new condition column, and I go to combine it, and it gives me this invalid index error. I'm going to show you the errors that I get so you see when I get this error, this is how I fix it. It's like invalid index. What's going on? Well, when we combined, you can see our index is 0, 1, 2, 0. So A, that's not unique. B, when I created this, our index was just this range index, says 0, 1, 2, 3. 0, 1, 2, 3. So I need to fix the index, which I'm going to use with just reset the index, .reset index. And now they both have that same range index, 0, 1, 2, 3, and I can now concat those rows on. So the takeaway here is concat uses the index labels to align your new data with your existing data. So if your indices are off, the concat won't work. So your indices are off, and you still want to merge your data. How can you do this? Well, we have .merge, and this is very similar to joining tables in ArcPy, or if you know SQL, this is basically SQL merging. SQL style joins with inner, outer, all these different methods. So I'm going to clean up my data frame. That's 5 minutes. And create a new data frame with a description. And now I'm going to do a .join, and you can see based on that surface type, I took the description and added it to my data frame. So if you've got a dictionary or some other thing that you want to join your data in to multiple rows, a many-to-one join, that's basically what we're doing here. We can do an outer join, keep all the rows, no matter whether they're missing in one data frame or another, and add an index or an indicator column. And this, I've seen examples to use to say, I need to know which of my keys are present in one but not the other. Well, do a merge and then look at this merge column to see, oh, it's only in the right data frame or it's only in the left data frame. So it's kind of a set operation on data frames. So what about spatial joins? Now, this is one of those things that I can do in ArcPy, but I'm going to do here in pandas as well. So how many people are there per supermarket in every county? So I'm going to load in our open source places data set for our supermarket data, and I'm going to load in our counties data. A couple slides showing how I'm trying to figure out which value is the supermarket, but ultimately I realize that it's the category, and I need everything that is supermarket in the category column. So I just copy that out to a new data frame. So you can see category, supermarket, and then we got a bunch of information. Importantly, we've got spatial data. We've got an X and Y point here. So now I'm just going to call .spatial.join. It's really that simple, except it isn't. I called it and I got an error. Exception, and this is a really long, oh no, this isn't the long one. So differing spatial reference. Crap, my spatial references aren't the same. It doesn't hold your hand, it doesn't reproject on the fly. So we need to look at our spatial references. So we say .spatial.sr, and you can see our supermarkets are in just WGS 84, while our parcels or our counties are in Web Mercator. So since points are easier to project than polygons, let's reproject our points to WGS 84, and then we'll do the join. Except, hey, big honkin' long key error. This goes about down to here. So if you look at the end, you see key error. It's giving all these different indices or values, not an index. This took me a second. What the heck is going on? Well, I realized that when we subsetted out the supermarket, it wasn't resetting the index. So now the supermarket still had this old index. Basically, the indices were misaligned. So I reset the index, and then I called the spatial join. And you can see now I've got category supermarket. I've also got all our county data in the same data frame. Now that it's in the same data frame, we can operate on it. So here I'm just doing that all in one call and saving it to a new data frame so we can operate on it. But you'll note I've just filtered down to just a few columns, because again, I don't want to get confused with all the different columns. So now we've just got name and last census attached to our supermarkets. And now that we've got those, we can call group by to get the count of every supermarket in each county, to sum the population of each county, or to get the population of each county. And now I can operate on those two columns to get our, or I'm going to put those in a data frame, then I'm just going to do some math to divide. And now, this is hairy, but I'm doing it all in one line. And this is what I meant by it. The syntax is a little confusing at first, but as you get experienced with it and start to understand this, and the formatting, these should be single lines, you can see how you can get really powerful code really concisely. There's not a lot of filler code in there getting in your way. So here's our people per supermarket, and kind of interesting, you know, Beaver actually has the best concentration of people per supermarket, but this could be because a lot of supermarkets are actually labeled as buildings in the data. So if you want to go fix this, go to OpenStreetMap, start retagging supermarkets, and that will make its way into our data. So that's the joy of using this data. But now I can join that back to my county data, which is spatial. And if you do this in the notebook, it will plot it out, and Bob's your uncle, there's your map, there's your data. You can save it to a feature class. You've now done a pretty complex analysis and gotten a feature class out of it that you can then do whatever you want with. So, in 1 minute, Esri spatial data frames. This is how we get all these spatial operations. And the way we get these is this import. From ArcGIS features, import GeoAccessor, GeoSeries Accessor. This is in the documentation, it's in here. But these add the .spatial attribute to our data frame. This is how I've been getting project, spatial join, load from feature class. So your pd.dataframe.spatial or your data frame name .spatial, and then you've got all these different functions. The cool thing about this, it doesn't require ArcPy. So if you're doing this on a server or somewhere that you don't have ArcGIS installed, it will use the open source Shapely library to do all the spatial operations. So this is similar to GeoPandas under the hood, but gives you access to all the Esri other stuff that Esri gives you with spatially enabled data frames, which gives you access to a lot of ArcGIS Online functionality. So if ArcPy is available, it'll use ArcPy. If it isn't, it uses Shapely. We load from feature class. We can also load directly from an AGL layer or from a data frame just containing lat longs. I do this a lot. If I get a CSV with lat longs, I can convert it straight to a spatially enabled data frame. These can be exported to feature sets, to feature classes, or straight to feature layers that can be uploaded to ArcGIS Online. Couple tips and tricks. Sometimes when you're performing these spatial operations like projecting or something, and then you go to perform another operation, it fails. And you're like, what? Everything should be good. Well, sometimes the way it sees what columns to use for spatial get a little confused. And so they provide this .validate method. And that will say, yes, everything looks good, or no, it doesn't. So if it's true, everything's great. If it's false, well, there's something broken. How do I fix it? First, make sure it's pointing to the right column for its geometry. And it's normally shape, and you can use that using .set geometry. Now, you might look at this thing, oh, I can store multiple columns in a data, or multiple geometry columns in a data frame. This would be awesome. Don't. I've tried that. It just gets confusing. Stuff breaks. Stick with a single geometry column per data frame. And then also, sometimes, especially Shapely, it alters the projection just a little bit. So normally the projection looks like this. A name and a projection number. With Shapely, that just becomes 0:3875. So, oh, it didn't show up. So instead, we can set this .sr equals, we've already projected it, so it's already in this. We're just setting this property so it knows what projection it's in. So, Whirlwind Tour, here are the resources I'm going to point you to. These are links. If you Google the Pandas user guide, there's 10 minutes to Pandas, an in-depth user guide. There's also the full API reference, so all the different functions you can get off of these. A website I really like is Real Python. They have some really good, easy to read, easy to follow tutorials for all sorts of different Python things, including Pandas. Some of them you have to pay for, but there's a decent amount that are free. So I highly recommend you check those out. And then tomorrow I'm going to talk about Pallet Jack. That uses what we call skids, and that uses a lot of Pandas under the hood. So to see how we're using Pandas, you can look at any of our skid repos. And this link, if you click on it, will take you straight there. So thank you so much for hanging in there with me. I know this has been a fire hose. I'll be at our table. Contact me directly. Again, gis.utah.gov/presentations. All the code, all the notes, it's all right there. So have fun. Go forth and program. Break things. Have fun. Play. Learn. And make cool maps. So
thanks again, Jacob.
That's what we got.